to the organizers for the opportunity to present some of my recent work. I'll say in a second, more details about what I'm gonna tell or talk about, but also I would like to thank the organizers for this wonderful thematic semester. I've been here on and off, a bit less than what I had hoped at the beginning, but it's been a wonderful experience. The talks have consistently been great. The vibe was great, and the exchanges I had outside of the talks were also fantastic. So thank you very much. It's been really a wonderful semester, and I'm very excited to see what happens at the next workshop. So right. So today I'm going to talk about a topic that is a good precursor maybe to the next workshop, which is a workshop about AI, maybe less so in terms of my age as not so young researcher anymore. I'm reached that age where I enjoy very much when people call me a young researcher, which means I guess I'm not anymore so much of one. But still, for the topic, it's very well aligned with what we're going to talk about in the next workshop. And the topic is, as you can infer from the title, transformers. So as you probably know, transformers are neural network architectures that are at the core of large language models, such as ChatGPT, Gemini, and all of your favorite models. And as you definitely know, these models have had a huge success in terms of, for instance, natural language processing. Although it's not still very clear how these models work on their input to achieve such a big success. So in particular, what kind of functions they are and how they elaborate their input through their depth to build some interesting representation of the data and achieve such a huge or unprecedented success. So in recent years, some works have appeared interpreting these machines, these neural networks, as functions acting on particles and identifying a phenomenon which is a clustering phenomenon of these particles as they move through the depth of this network. And I'm going to give much more detail about this in a second. But the idea of the talk is to give a bit of context about this line of research and to state some new results along this line of research, in particular, giving some precise mathematical results about this clustering phenomenon and being able to, in some idealized regimes, characterize it more precisely. Okay, so this is going to be the topic of the talk. All right. So the talk has to do with dynamical systems, in particular continuous time dynamical systems. Please do stop me at any time if you have any questions about what's being presented. I think the audience is quite varied in terms of background, so I'm very happy to give more specifics or more intuition about some of the steps. This is joint work with Giuseppe Bruno, a PhD student at the University of Bern, and Federico Pasqualotto at UCSD. All right, so in order to start, we're going to talk about neural networks. So let me not start with transformers, but start a step before. So we're going to talk about deep neural networks, and let me start by talking about residual neural networks, which are a specific type of deep neural network. So in general, what you expect a deep neural network to do is to take an input, which in this case is a picture. You will take this input, embed it into potentially or usually a high-dimensional space, right? For instance, the picture, you can take the RGB profile and then just map it to RD. Then what you will do is you will pass this picture through to the network. This network will act layer by layer in the feed-forward case on this picture. And at the end, the output of the network will be passed through a usually classical machine learning step, which is maybe classification, or softmax classification to infer that this is actually a cat. Okay, so this is what happens in feed-forward neural networks. What in the jargon people say is that this feed-forward neural network will work through the depth of the input on the input through its depth, building a representation of this input that then ideally is going to be easy to classify at the classification step, so at the output of the layer, right? So for instance, you may imagine that a cat, when it's input to the network and the the representation of the cat, which is the value of the hidden state of the network, travels or evolves through the depth of the network, will evolve to a different space or part of state space if this is going to be a cat or if it's a dog in a different part of state space, in order to make this classification step as easy as possible. Okay, so concretely, this is done in residual neural networks in the following way. You update the hidden state of the neural network by taking the state at the previous layer and then combining additively this state with a nonlinear function f theta, which is, again, the layer-wise update of the network. Okay, so here, residual in this, so the name residual comes from the fact that you have a residuum from your previous hidden state, and then you combine this with a small epsilon is going to be a small update parameter times a neural network on a highly nonlinear function, which depends on the parameter of the network theta. And the dependence on theta here doesn't matter at all. We're just going to focus on the effect of this update on the representation of the state in the network. Okay, so this is going to be the general idea of the talk. The general idea is that I want at inference time, so I'm assuming the parameters of the network have been trained, I want to understand how this representation of the network evolves through its depth, and to characterize the output state or the pre-output state in a way that makes it easy for me to understand that then the classification step is easy. Okay, so what I will focus on in this talk is this part of the network, the layer update through its depth. All right, this is going to be the main idea. And of course, this can be done for residual neural networks and then for transformers. Let's stay first with residual neural networks. So as a summary to what I said before, earlier we have an input data which has been already encoded in a high-dimensional real space, x0. And then the hidden state of the network, the representation of this data, evolves through its depth according to this discrete time update. Okay? Here, f theta is a fit for a neural network, and epsilon, as I said, is a small positive parameter. This can be represented graphically with this form. Okay, so we have an input, and then we have a L time where big L is going to be the depth of the network. Okay, yeah, sure.
F is usually like a convolutional layer, right, rather than.
It could be, or it could be fully connected. I mean, yeah, it doesn't really matter for this talk. Yeah. Big L is going to be the depth of the network, and then you iterate, right, the application of this recursion, where you pass the input or the output of the previous layer through a fit-for neural network, and then you add it with the input of that network to prepare the representation for the next layer. Yes, please. In this context and throughout this talk, we will consider the parameters as layer constant. Yes. So this is the context of weight sharing. With some work, you can extend this reasoning to everything I'm going to say. You can extend it to, under reasonable assumptions, to non-constant parameters. Yeah. Thank you that's great. I love interactions. Okay, so the idea is now that one can, and this is what has been done in 2017 and onwards, one can make sense of this update and develop some intuition about how these representations evolve in the depth when one takes the deep limit of this network. So we were going to take the limit where big L goes to infinity, and we will scale, as it's typically done, epsilon as 1 over L. So as we will scale epsilon, the time step of the update, accordingly, and letting L go to infinity, we will have that this dynamics converges to the solution of a differential equation. This is very apparent for those of you who are expert in, let's say, numerical integrations of ODEs, right? This is just the Euler method. Or if you're not expert in that, you can just look at this. So what I did from the previous slide is I moved XL to the left-hand side. You can consider this divided by epsilon as a derivative, right? And then the time derivative of X is equal to F, which is exactly the ODE that you get in this update. Okay. Yet another way to see this is really a pictorial representation of this. So F is the vector field that you have in this space. This is RD. the trajectory of the ODE system is the blue trajectory, so it's integration along the lines of the vector field. And if you take the tangent to the vector field at each step and you decrease epsilon, increasing the number of time steps accordingly, you will have a trajectory that follows closer and closer the trajectory you want to mimic. Okay, so this is to convince you that there is a formulation which is called the neural ODE formulation that allows you to capture what happens in this discrete time dynamical system setting in a continuous time limit. Okay, and this is what tells you how the representation of your data evolves through the depth of the network, and you would like to understand what f here does to your data. Okay, and this is again the context to setting the stage for what we really care about in this presentation, which is transformers. Okay, so transformers, I don't think I need to tell you, motivate the use of transformers. Transformers are used throughout. This is just 2024, but you can see the number of models has increased exponentially. And these are all the large language models, some of the large language models that have used transformers as architecture to achieve the, again, very significant success that we have observed in recent years. And the structure of the neural network that has allowed historically this success is what is represented here. So please don't be scared. I'm going to explain this in detail, but basically there is some similarities with the structure I have just introduced, in the sense that, again, you have a layer-wise L-time application of a discrete time update of the hidden state of your system. And again, what we want to consider in this talk is how this system evolves and how your data evolves through the depth of the network, to try to explain how this network, again, work on their data and partially explain, give an intuition on how this can be so successful. All right? Okay, so we want to do exactly what I did earlier about the residual neural networks and transpose this idea to the transformer setting. Right? So as you can see, again, this architecture looks a bit more complicated, and indeed it is more complicated, but it has the same blocks. Okay, so first of all, remember, in the cat setting, you have embedded the cat in a high-dimensional space, and this is what is done in this part of the transformer. Okay, so what happens here is you give the transformer a sentence, which is, for instance, write a new paper on blah, blah, please. Obviously, you finish with please because you want, when they will take over, you want to be on the good side of things, right? And then what you will do is you take this sentence, you combine each element of this sentence with a positional encoding, so a code that tells you where each word sits inside the sentence, right? And here we will consider sentences of size n, and then each of these elements is going to be considered as a token, right? Token is the word that you can interchangeably use with word of the input in this talk. Okay? So again, you have a sentence, you divide it into tokens. To each token, you associate a positional encoding telling you where this token sits in the sentence. And then the second step is you embed each one of these new objects into a high-dimensional space, right? This embedding step is a very complicated, non-linear step that we are not going to focus on. All you need to know is that there is a very complicated function that takes each one of these elements and maps it to a high-dimensional space, which in this case we'll assume to be just a sphere. Okay, so the d-dimensional sphere. Why this is the case will become clear in a second. Okay, so we have input divided into tokens, tokens associated to a positional encoding mapped into a high-dimensional space. And the result of this operation is that I have transformed an input sequence into a list of tokens, which now live in this high-dimensional space of length big N, where big N, again, is the length of the sentence that I have given as an input of the network. So far, so good? Okay. So these guys are going to be distributed somehow on the sphere in dimension d. D you can think about as being high. And the important point to be made here is that these elements are interchangeable, meaning that it is true that each word has a meaning depending on the position of that word in the sentence, but I have already stored the information contained in the position of the associated word in the position of X on the sphere, right? Because I have associated to each word its positional encoding explicitly, okay? What I mean here is that if I interchanged A and right, the 2 and 1 would be interchanged, and this would result into different position of X1 and X2, not just the interchange of their position in the list, okay? So let me repeat, the position of each word in the sentence is encoded in the position of X on the sphere, not in its position, not on its index. So these are interchangeable objects, and therefore can be interpreted as particles. Okay, so I will interpret these guys as particles sitting on the sphere throughout the rest of this presentation. Discrete measure, yes. Absolutely, yes. All right, great. So now that we have talked about the positional encoding, let me move to the actual, operation that this architecture applies to these elements. So to this list of particles. And again, exactly as before, we have a reiterated operation of a discrete time dynamical system. And at each layer, what we'll have is, first of all, we'll apply the so-called self-attention mechanism. Okay, so this, don't be scared about this formula. We'll significantly simplify it for you in a second. Okay, of course, if you're familiar with it, then you're happy, right? This is just a softmax average of the position of each particle. Otherwise, you can just look at this formula as a complicated function that I will simplify in a second, updating or taking a particle xi and updating or giving as output a new position xi hat that depends on the position of xi, but also on the position of the other particles xj's, right? So you're taking a weighted average of the position of these xj's, okay? And here you have some parameters popping up. Of course, here z is a normalization factor. Q, K, and V are some parameters that I will remove from this model in a second. For the first part of the presentation, the only important parameter here is going to be beta, which is the inverse temperature, and controls essentially the importance of this exponential in this expression. Okay? All right, so for each particle, you get this output, and then exactly as before, you combine it additively with the input of the nonlinear of the neural network, right? Which in this case is or the nonlinear function, which in this case is given by this function here, in this way. And the difference with respect to the other difference with respect to earlier, so the feed-forward case, is that in this case, you have to map things back onto the sphere. So this is called post-layer normalization step. And it's just, instead of taking x plus epsilon x hat obtained through here, you have to map it back on the sphere. So to make sure that every particle stays on that space, right? And that also explains why in the first place we have made that assumption. Okay? Great, so this is what summarizes this operation. So you apply this L times. So usually you intercalate this operation with another feed-forward neural network that acts independently on each of the particles. But for this, the sake of this talk, we will completely forget about this part of the network. So I want to focus on the effect of self-attention, which is this operation here, on the evolution of these tokens, right, of these particles through the depth of the network, forgetting about the feed-forward layer, because self-attention is the main innovation, if you want, in this architecture. All right, so as a summary, then a transformer can be interpreted as the iterated application as a discrete time dynamical system where at each layer, each particle is updated by combining the input of the layer to the output and then taking the norm in an additive way and then taking the norm. Okay, so you have this very complicated formula that tells you how these particles move through the depth of the layer, through the depth of the transformer, and again, this is an interacting particle system in the sense that the position of xi at the next layer doesn't depend only on xi, but also on the position of all the other particles that are present in the system. All right, and then exactly as before, you can take an infinite depth limit and obtain from this discrete time dynamical system, you take out the xi update, and this is the nonlinear part that will give you the differential in the continuous time limit. So again, exactly as before, you take the infinite depth limit and you obtain a continuous time dynamical system describing the evolution of each one of these particles through the depth of the network. and this is given by this formula, right? Here, the difference, notice the presence of a projection operator, Px, which tells you essentially, results from the fact that you want this dynamics to be constrained on the surface on the sphere, so the differential needs to be on the tangent space of the sphere to respect that constraint, and it results from this n. All right, so now that I've presented you a very complicated dynamical system that we don't want to go into detail about, I want to try to understand or develop some intuition about how this dynamical system works in continuous time by making some simplifying assumptions. Okay, so the first assumption that I will make is that all the parameter matrices of these models are going to be the identity. So I'm going to simplify this part of the model and just assume that all of the parameters are just the identity. All right. The second part is, the second simplification is to substitute the normalization factor in this part of the of the update, which is particle dependent. See, there is a dependence on I here with a common normalization factor of 1 over n. Right? This makes me very happy as a probabilist because then I can see this representation as or this this expression as just integration against an empirical measure. And as a byproduct, this also allows me to phrase this dynamical update as a so-called gradient flow. Okay, so I can rewrite the differential, so the evolution of each one of these particles, as the gradient of a certain energy under these assumptions, right? And this gradient this energy is simply given by this expression. So we have a sum over all pairs of particles of an exponential of the inner product between these two particles. All right? Okay, so now we have a gradient flow, and now we can identify essentially the fixed point of this dynamics, so the long time behavior of this dynamics, with the critical points of this energy. Okay? So let me try to study a little bit what the critical points of this energy are. Here you have a pairwise interactions, and this xi and xj's are limited on the sphere. So there is a global upper bound on this inner product, which is 1. And this energy is maximized when all of the particles sit in the same position on the sphere. So when all the particles are in a synchronized state. This will maximize the energy. And since this is a gradient ascent algorithm, so this pushes each particle in the direction of steepest ascent of this energy, this you would expect are the long time limits of this dynamics, right? So you would expect these particles to maximize the energy, so to get closer and closer to each other until they reach a state where this energy is maximized. They're all in the same condition, so they have clustered, they have completely synchronized. Okay? And this is the main intuition of what you can say about this dynamics. Is this representation clear? This is important for later. Okay, so again, we have a continuous time dynamical system, moving particles. This is the gradient flow, upwards gradient flow of an energy, and this energy is maximized when all particles are in the same position. So these particles try to cluster together, try to converge to the same position. Yeah?
Is it something that generalizes well with other matrices?
You can generalize this provided that K transpose Q is equal to V. You have exactly the same structure. In the other case, this doesn't necessarily happen. So you have to decompose your dynamics in a conservative and a dissipative part. The dissipative part will have something like this, but the the conservative part may have some non-reversible dynamics. So let's say a limit cycle or something. So it can be much more complicated. This is definitely a strong assumption that I'm making here. But let me stress that the qualitative dynamics that one observes under this assumption are very close and very similar to the qualitative dynamics that one observes in practice or the phenomenon that I'm going to describe is very close to the one that people observe in practice. All right. So before moving on, let me make another important remark here. The important remark is that this dynamics is so this energy is invariant under a joint rotation of all of these particles. So the rotational symmetries are preserved by this dynamic. So if I start with an initial condition that has a certain rotational symmetry, this rotational symmetry is going to be preserved by these dynamics for all positive times. And this is going to be important later. Okay, so let me try to now push a bit in terms of what one expects for these dynamics. So like we said, we have an energy. We are aiming to maximize this energy. The maximizer are single points. And indeed, it has been shown in a sequence of works that for finite number of particles, the dynamics converge for almost every initial conditions to limit points that are indeed totally synchronized. So to points where all the particles sit in a single cluster. All right? This, again, let's try to frame this in the context of representation. This corresponds to thinking about what happens in a transformer as taking very complicated input message and then transforming and simplifying it into a very simple concept or context that the transformer has identified from its input. Okay, and that concept corresponds to where the cluster resulting from these tokens is on the sphere. Okay, so these works basically have shown that the long-term dynamics of this, of the long-term behavior of these dynamics is converging to a single cluster for almost every initial condition. But this is not really the end of the story, okay? Because if one runs some simulations, what one identifies or what one sees is that indeed, if one starts, for instance, from a uniformly IID distributed set of tokens on the sphere, and then runs the simulation for a long amount of time, one does indeed identify the convergence to a single cluster. But what precedes this convergence is an intermediate phase where particles cluster up into metastable clusters on the sphere, which then sequentially merge to form the final and totally stable cluster that we have identified earlier. Yes? This is with the assumptions that I made before, although let me just mention that if one runs BERT, which is a very old model, essentially, one does see a clustering phenomenon. So what I'm plotting here as a function of the layer depth are token-to-token alignment, so the inner product between tokens. And you do see that you develop a peak, even though it's not that clear, so it's not just one peak, but qualitatively you do observe the development of a peak, meaning that many particles do indeed align in a certain sense. All right? Yeah, please.
The cluster depends on the initial condition.
Yes. Yeah, absolutely. Okay, so if you think about it, this is actually a more sensible picture of what happens in a transformer. So this intermediate phase is a more sensible picture of what happens in a transformer, because a transformer doesn't really, so if you think about these clusters as representations of what your input message has been understood to be by the transformer, it's more, so a representation that is formed or that consists of a certain set of clusters, it's a much richer representation than simply a single cluster that develops in the very long time behavior. So in a way, it makes much more sense to try to characterize this phase rather than the long time behavior of the transformer, also because these things are not really infinitely deep. They have a finite depth, so you would expect, to observe something that happens a finite time in this dynamics. Okay, so what we would like to do in the rest of the talk, at least in the first part, and let's see if we have time for the second part, is to look at what happens. So try to explain this metastable, the emergence of this metastable clustering structure that then, as expected by the previous works, will converge to a totally clustered state. Yes.
Essentially, you only have attractive couplings in a way between the.
Yes.
So if you would put matrices with negative entries, then you would have repulsive clusters as well, right?
Yes, that's indeed possible. Yeah. Yes. But again, there is some truth, because of the plots I've shown earlier, there is some truth to this story in practice, right? So again, this is a very idealized regime where we are able to make some precise mathematical statements, but there are a lot of open questions that are still very interesting to tackle. In particular, relaxing this strong assumption on the parameter seems to be a very important aspect of it. Yeah. Okay, so right, so and in particular, sorry, before moving on, the regime where I want to establish this result is I want to characterize this intermediate and metastable clustering phase in the limit as n goes to infinity and for values of beta that are fixed. Okay, so and I would like to characterize this structure as a function of the value of beta. Okay, so just to give you a more graphical representation of what happens in this case, if you start from, again, an initial condition that is a uniform distribution for a large number of particles. Again, I'm assuming uniform distribution because I don't have a favorite direction on this manifold. Then what you will observe is that the first evolution of this system is clustering particles into these smaller clusters, and then this metastable or smaller clusters will sequentially merge, like you can observe here, and eventually, given long enough time, they will converge to a fixed point and a unique cluster, right? And we want to characterize this structure emerging from the dynamics from the uniform IID initial condition. All right, so let's say something that is very natural for, this was apparent in the first slide. Let's try to frame this into a more mathematical discussion. First of all, I would like to discuss the dynamics of a quantity that I want to take the limit of. So I want to take the limit of large number of particles, and the natural quantity to observe here is the empirical measure, because there is a well-established notion of convergence of empirical measure in space of probability measures, right? And then what I can see is that because of this 1 over n sum over particles structure of the interaction field, this is a mean field, as people call it, interaction, and this can be expressed easily as simply the integral of a certain interaction kernel against the empirical measure of the particles, right? So you can express the vector field as a function of the empirical measure. And in particular, as I said before, this vector field is has a gradient structure. So I can express this as the gradient of a certain interaction kernel, right? So this gives me the evolution of each particle, which is carried by this vector field. And the evolution of the associated empirical measure can be then written as a partial differential equation, that does exactly what this vector field does. So if you're not familiar with partial differential equation, that's not a problem. All you have to accept is that if you are moving particles along this vector field, which depends on the measure, then the associated empirical measure evolves according to this partial differential equation containing the same vector field in its right-hand side. Okay, so this is just transporting particles along this vector field, right? So we want to study the evolution of this empirical measure along the trajectories of this PDE. And again, exactly as before, because of the gradient structure of the original vector field, one can say something about the trajectories of this partial differential equation. In particular, you can frame this as a Wasserstein gradient flow of a certain energy E, which is the energy that I listed earlier, or you can re-express that energy using a double integral against the empirical measure. And then you can show that there is a unique global maximizer of this empirical measure, which is the uniform measure on the sphere, so where particles are uniformly distributed on the sphere. And then you have a global maximizer, so where the dynamics is trying to go, which is a single Dirac delta at a certain point on the sphere. And this is where the dynamics will try to converge. Okay, this is consistent with what we have said earlier. Okay. Notice, however, that because the uniform measure is a global maximizer of this energy, the uniform measure will in particular be a fixed point of this dynamic, so it will not move. Oh, this is sorry. This is no. Yes. All right. So let's try to move on from this and try to take the limit, right? So I want to study the evolution of a large number of particles as we had anticipated earlier. And this means that I am trying to sample particles IID from the uniform measure, which is the Lebesgue measure on the sphere. And as n goes to infinity, because of the law of large numbers, this will converge towards the measure I'm sampling from, right? And then what I'm trying to do is I'm trying to evolve this IAD sample from the measure forward in time to observe what kind of resulting structure I observe in my dynamics, right? So what happens here is that because the uniform measure is invariant under this PDE, what will happen is that over finite time intervals at least, the evolution of the sample from the uniform measure, which converges to the uniform measure, will stay close to the trajectory of the limiting, or to the limiting trajectory, which is a fixed point. So over finite time intervals, nothing will happen in this system, essentially, right? So essentially, the analogy here, the finite dimensional analogy, is that I have a maximum of or a minimum of my energy in the case of I'm trying to maximize the energy. I have a minimum, which is a fixed point, and I have a sequence of points that converge to this minimum. These are the empirical measures that converge there, right? So over finite time intervals, as n goes to infinity, the evolution of my initial condition will remain in this interval because they converge to a fixed point, and therefore they stay close to that fixed point for finite time intervals. So what we need to do in order to observe this clustering phenomenon is to look at these dynamics over a longer time horizon, an horizon that allows me to exit, so allows my sequence of initial conditions to exit from this neighborhood of this fixed point. Is that clear? So I'm sampling from a uniform condition. This uniform condition is a fixed point. So over finite time horizon, something that starts very closely from that fixed point will not move. So in order to see some macroscopic structure emerge from this dynamics, I need to look over longer time horizons. All right, and in order to do so, like every sensible, physicist or mathematician would do, what one does is one linearizes the system close to the unstable fixed point and observes what happens to these dynamics. And this is exactly what we are going to do now, okay? So in order to capture the emergence of this metastable clustering phenomenon, what I will do is I will take the following, I will do the following analogy, draw the following analogy. So we will have a totally unstable initial condition lambda, okay? We will have a sequence of points that as n goes to infinity converges to this initial condition, right? And then what I will do is I will take my dynamics and I will linearize these dynamics close to this totally unstable fixed point, right? So what it means is that I will take a linear approximation of the dynamics and I will diagonalize this linear operator that is on the right-hand side of my differential equation. And what will result from this linearization is an eigendecomposition, okay, that gives you a set of eigenvalues and a corresponding set of eigenvectors, right? This is what happens in finite dimension, right? So let's say d is equal to 2, right? And to this set of eigenvalues and eigenvectors corresponds a set of growth rates and growth directions, or growth modes, right? And when you start, and some of them will be stronger, let's say, and some of them will be weaker, okay? So what will happen in this case then is that there will be a dominant growth rate, right? There will be one that is stronger than all the others. And as you start closer and closer to this initial condition, your dynamics will be well approximated by, let's say that this is xn, okay? You will have that xn as a function of t is equal to xn, approximately equal to xn as a function at time 0 times e to the lambda max t. So you have an exponential growth rate, approximately, along the direction, an exponential growth rate at the rate of the largest eigenvalue of the linear operator. And the direction at which this will happen is going to be in the direction of Vmax, which is the dominant eigenvector of the dynamics you're trying to look at. Yeah. Yeah, I will do it in the next. Right. So I don't have an explicit expression for that. But so, I mean, I could write an explicit expression, but I don't think I have it on the slides. But the operator that I want to study is, oops, sorry, it's this. It's this. Okay, yeah. Yeah, absolutely. But really, I mean, the analogy here is x dot equal to ax, where a is going to be the linearization of this operator here, right? And then this operator can be diagonalized into a set of growth modes and growth rates. And the dominant one is the one that will grow the fastest and therefore will control the growth of these conditions as they exit from a neighborhood of this totally unstable initial condition. Yes?
And maybe also by the equation xn of t is approximately max like exponential of max t.
Mm-hmm.
So what is xn of t will not have been?
Sure. So the actual, so there is an additional multiplicative term here, which is xn of 0 v max. So what you're doing here is you're decomposing A into eigen, so this is equal to sum of Vj product x times e to the lambda. So the solution x is equal to this, e to the lambda t, lambda jt, right? This is the decomposition, and since there is one that grows much faster than the other ones, it will control this growth, and therefore macroscopically, as I exit a neighborhood of this point, the state that I will observe will be dominated by the fastest growing eigenvalue of this dynamics. Yeah.
Here you are taking two limits, like once t is going to be sufficiently large.
Yes.
Escape from the stable.
Exactly. Exactly. So here you have convergence of xn 0 is of the minus x infinity is of the order of 1 over square root of n in the right topology. So you have IID. This is a central limit theorem basically, and then if you plug this into this expression and you solve for xn order 1, you will see that the time that it takes you is of the order of log n. So if I look at times of order log n, I will observe a macroscopic fluctuation that is going to be dominated by the largest growth mode, which is the one I will identify. Yes?
What about the multiplicity of lambda max?
That's a great question. So let me move on. It's exactly where I'm going. So I'm super happy that this sounds interesting. So right. So this is a finite dimensional analogy, and this is the infinite dimensional analogous that we do in this case. I'm going to present the results in the setting of d equal to 2 because they are simpler to present, and then I will discuss briefly what happens in higher dimensions. Okay. So again, first of all, I diagonalize my operator, which means I'm decomposing the right-hand side, which is the divergence mu times v of mu, into a linear and a remainder term. Okay. The linear term, the linearization, happens to be diagonalizable in the Fourier basis. Again, we are in dimension 2, so everything is very simple here. Okay, so the vectors v max are simply cosines. Okay, in this case, because everything is true up to a rotation. So I just need one of the two elements of the basis of the Fourier space. And then the eigenvalues, which are what selects which modes will grow the fastest, are explicit in the sense that they depend on k, the index of the mode, and on an inner product between Gegenbauer polynomials, which are pk, so this is a given set of polynomials, and an expression which depends or captures essentially our interaction kernel, right? The important thing here is that the expression is explicit and is given by the Bessel functions of the second kind, okay? So it doesn't really, of the first kind. It doesn't really matter. gamma k are explicit and are explicit functions of the index and of beta, which is the free parameter in my model. Okay? So I can explicitly compute this ik. And like David was exactly saying, I'm going to assume, which is generic in this case, that beta is chosen such that this gamma k, so the dominant eigenvalue, so the dominant growth rate is unique. So it maximizes a unique gamma k. This is generically true because we know how this function, what this function is, and this function is a function that is like this. So it's a unimodal, and I can, so it's evaluated at discrete steps, and so there is going to be generically only one element that maximizes this, this quantity. Okay? So if this is true, so under this assumption, so I can choose the beta, so sorry, fixing a beta, I can identify the fastest growing eigenvalue, the fastest rate corresponding to the fastest growing eigenvector, which is the cosine. And this will be the mode that they will observe exiting from a neighborhood of my initial condition. Okay, so as n goes to infinity, given sufficient time, under this assumption, there will be a unique mode that will grow faster. I will have the emergence of some structure from a totally unstructured initial condition, which is essentially the uniform measure. And I can characterize which structure this is based on my parameter, right? Because again, choosing a parameter beta, I can identify the fastest growing rate. That fastest growing rate corresponds to a fastest growing mode, K max, okay? And then K max is the number of modes that I will observe exiting from my totally unstructured initial condition. And in the limit n goes to infinity, I will recover exactly this structured initial condition. So this structure emerging from my dynamics given sufficiently large times. Okay? This, however, does not, strictly speaking, correspond to a clustering phenomenon, right? I was talking about clustering, but here I'm just telling you that from the initial condition, I have identified some structure that points, you know, in the direction of a certain number of clusters appearing in my dynamics. I haven't proven that this is actually what happens, so I don't have a proof that tells me that from this K-max periodic initial condition, I will converge to this K-max periodic clustered state. Although, given some previous results, this seems like a very, very reasonable and actually quite fastidious fact. It's not, so very reasonable assumption, and it's actually a quite fastidious fact that we cannot prove this, right? So here what we have is a characterization of the structure emerging from the transformer dynamics in a essentially structured pre-clustered phase. The connection between the pre-clustered phase that has a certain periodicity, which again needs to be respected by the dynamics, to the corresponding k-periodic cluster state is still open. So we make that as an assumption, right? So let me say again what we have here. This is a result that tells us what is the structure of the emerging clustered state that we expect, and we can characterize that as a function of beta. What is still open is to connect this clearly structured new initial condition, which has a certain periodicity of K max, to the corresponding totally clustered state. And this is not yet. Beyond this T1, yes. That corresponds to a very nonlinear dynamics, and it's very hard to connect the two things. What I should state, though, is that one can do a reasoning, which is one can look at only one periodicity cell of this dynamics and then look at the evolution of that periodicity cell. And for this initial condition, so actually from the results that I stated earlier, almost every initial condition on the circle converges to a single delta, right? So if I now take one periodicity cell of this dynamics, I map it back to the circle, I evolve that, right? I would expect that for almost every initial condition that converges to a delta. And then wrapping it back on, this corresponds to the fact that we would have 5 deltas in this case, right? With a 5 periodic initial condition. And this result holds for almost every initial condition, but not for, we cannot show that this initial condition is not among the ones that does not satisfy this assumption, right? So there is a very strong result that suggests that this is the case. So you have convergence from this state to that state, but this result holds for almost every initial condition, and we cannot rule out that this one is in that space of measure 0 initial conditions that does not respect those assumptions. So this connection is still open. However, numerically, one can show that this seems to happen. So let me show you some numerical experiments here. We start with 2 choices of beta, for which we plot the associated eigenvalues of the linearized operator, right? So gamma k as a function of k for 2 values of beta. We see that for beta equal to 5, the dominant eigenvalue is the 3rd eigenvalue, so corresponding to the Fourier mode of index 3, while here we have the dominant eigenvalue being number 4, so a Fourier mode of index 4. So in this situation for beta equal to 5, we expect some structure emerging with 3 clusters, and in the other case with 4 clusters. And if you run the dynamics, you observe exactly that, right? So you observe that, of course, this is finite depth again, right? But this, you start from a IID uniform initial condition, and in the first line for beta equal to 5, you observe the emergence of 4 clusters, 3 clusters, and in the other case, the emergence of 4. So this kind of corroborates the idea of that I presented of the emergence of a structured metastable cluster state from a totally unstructured initial condition. All right, so are there any questions so far? So this is a result in dimension 2. Coming back to the question by David, one would like to go to higher dimensions, right? And the same story actually applies equally well in higher dimension with an important caveat. One wants to take the linear operator, right, exactly like I did before, diagonalize it, and identify the leading eigenvalues as a function of beta. The problem is that in higher dimension, what was, since we are on the sphere, what was the Fourier basis now becomes the spherical harmonics basis, right? And it turns out that the linear operator diagonalizes also in the spherical harmonic basis, so that's great, but that eigenvalues associated to that linear operator have some degeneracy. So they only depend, as you can see in this expression, on the first of the 2 index, on the degree of the spherical harmonics. So all spherical harmonics with the same degree will have the same eigenvalue with respect to this operator, so they will all grow at the same rate. And so you don't know what exactly is going to be the structure emerging in higher dimensions because you have multiple modes growing at the same rate, right? So what we expect is that at least at the, at the emergent phase, so at the phase that I presented earlier, you have a random superposition of spherical harmonics emerging from these dynamics, all of the same degree, which is the degree K max identified by the linearized analysis I presented earlier. But then you don't know exactly which elements, so where this random superposition of spherical harmonics will converge, right? While before, earlier, it was pretty clear that a 3 periodic or a 4 periodic initial condition will converge to 4 clusters. It's pretty unclear in this case what any element of these random superpositions will converge to in terms of clustered state. So this is still a very open question. We know that the clustered state belong to this space. So this is the condition that tells you what, that gives you a metastability condition of the clustered state that has emerged in your dynamics in higher dimensions. So all elements of this space are fixed point of the dynamics, metastable fixed points of the dynamics. So it's what you will expect the dynamics to converge to on the given time scale, but which one of these elements corresponds to which one of these random superpositions, it's still very much open. Yes, please.
Just to make sure,
that it's some kind of Laplace operator?
Yeah, something like that. Yeah, it's not really a Laplace operator, but I mean the Laplace operator is an example of an operator of a linear operator that is diagonalized by spherical harmonics, but it's really a question of symmetry, right? I mean, an operator that is invariant under symmetries will always be, under rotational symmetries on the sphere, will always be diagonalized by the spherical harmonics. Take, for instance, the Hamiltonian of the Schrödinger Hamiltonian for the hydrogen atom. That's not the Laplacian, but it's still diagonalized by spherical harmonics. So it's a question of symmetry of the operator. Yeah, the eigenvalue is changing. Yeah. All right, so I think I still have 5 minutes. I mean, there is the last part of the talk, which I can go if people are interested, but I can also stop. No? I'll go. Okay. Okay, so right, so there's another regime now that I would like to briefly talk about. This is more recent work, actually. The previous one is already published, and this is more recent stuff. So, like many of you mentioned, there is something very unsatisfactory. There are many things that are very unsatisfactory about this model, actually. But one particular thing is that one has to make very strong assumptions about the fact that Q, K, and V are the identity. And actually, if you go to someone that really works with these models, also the fact that I mean, the normalization factor is simplified also is pretty disturbing. Okay, so we would like to keep those assumptions now and not make the assumption that Q, K, and V are the identity and Z is just equal to all particles, right? Yeah.
Does it really matter that much, given that you are getting quite good results with linear extension and things like this now, which is essentially like an unnormalized Taylor approximation of self-tax extension?
That's a good question. So I don't know. So okay. So people have run these models with and without the normalization thing. And in fact, what this normalization can be interpreted as is just a particle-dependent time change. So qualitatively, the answer is no. I mean, it's probably it's very strongly arguable actually that this effect that we're trying to characterize doesn't really depend much on whether Z is there or not. But since it's actually there, why not model it? So I agree with you. So the most important thing for me is to factor Q, K, and V in my analysis for real, not giving them as the identity. All right. However, we need to sacrifice something here because, as you can have seen, the analysis in the previous case was already quite difficult. So if I also add Q, K, and V, I lose a lot of the structure that I could use. And well, we don't see how to do that quite right now. So I will have to make a stronger assumption somewhere else. And the stronger assumption that I'm willing to make is that I'm not taking only n to infinity, but I'm also taking beta going to the infinity. And this is justified by some more recent models. I think Llama 4 uses them, for instance, where beta is actually beta is actually chosen as logarithm of n. So in reality, people actually do this, right? So they do. It's not an unreasonable mathematician's assumption here. People actually do take beta as a function of n sometimes. Okay. All right, and then I would like to know what happens to this dynamics. So in particular, I would like to characterize some sort of dimensionality reduction or clustering for this dynamics in this limit. So as n goes to infinity, beta depends on n and goes to infinity, but for general Q, K, and V. Okay, so very quickly, what will happen is that I have a vector field moving my particles, just as before. And what I did here is I worked out a little bit, made a couple of small changes with respect to before. So first of all, I have represented the vector field, the sums popping up as an integral against the empirical measure. That's totally legit, no problem here. Second thing I did is I multiplied by b minus 1/2 above and below. That's also just a scalar constant, doesn't change anything. And the third thing I did is I factor k on the other side of the inner product. Now it's ktqx times y, okay? But this is just an algebraic manipulation of what we had earlier. And again, I would like to study what happens to this vector field v as beta goes to infinity, okay? Now, what will happen is that I can do what is called the Laplace approximation. So I can look at this integrals. When beta goes to infinity, this e to the beta zy times beta to the minus 1/2 can be interpreted as the spherical equivalent of the Gaussian or normal distribution, right? And beta here is the inverse of the variance. So if beta goes to infinity, the variance goes to 0. So I'm taking particles that are talking to each other over a smaller and smaller radius, let's say. The other particles become irrelevant for these particles, right? So the interaction kernel essentially becomes more and more peaked. This is the limit I'm trying to take here, okay? And to first order approximation, what I can do is I can do, again, Laplace approximation, so approximate the integral of an f against this spherical Gaussian with f evaluated at z, where z is the blue part in the expression, right? And here, what I do is then I do exactly that. So I integrate the above and below term. So I evaluate the above and below term, assuming that mu has a density, right? Like so. Oh, sorry, here there is a q. This is a mistake. It's ktq also here. It's in blue. I obtain a way simpler formula here, and then I can simplify the numerator and denominator that are common and obtain a vector field that is given simply by this expression. Okay? So if I now look at this is the leading order expansion for large beta of the vector field moving the particles. And what I can do is I can then look at the long time dynamics obtained by evolving the particles along this vector field. Note that this vector field, sorry, let me go back real quick. This vector field has no dependence on mu. So the particles in this limit really don't interact. Okay, this is a much, much simpler dynamics that one obtains. And if one evolves the associated empirical measure according to this vector field, one obtains that it's pretty easy to see, although one needs a couple of lines of computation, so I will drop this for this presentation. One sees that these dynamics will push your particles to a low-dimensional state, or low-dimensional space, which is the leading order or the dominant eigenspace of the matrix moving the particles. KTQV is what appears inside here. Oh, sorry, VKTQ, sorry. VKTQ is the real matrix. Okay, so this will appear in this simulation that I am about to show. So in this simulation, I have identified VKTQ as having one leading eigenvalue. And what the dynamics does is it really pushes all the particles to the space where which in this case was aligned with the z direction. So it will push all the particles to cluster up in those dimensions, or in the directions of the leading eigenvalues of the matrix, which is given by KTQ. And this result holds for all choices of KT and Q, right? So you do, in this limit, have a stronger result, assuming that, again, you take the interaction as the interaction range to scale with n. Right, and then finally, let me just try to tie the two things together. So what happens in this case is that, so in this limit when beta goes to infinity, is that, of course, you can have one leading order eigenvalue of VKTQ and then have, obviously, your wonderful clustering dynamics along one direction. But in general, you could have a richer degeneracy of the leading order eigenvalues. So it could be that your dynamics compacts down or aligns down to a lower dimensional space. And then in that space, your particles interact according to the original interacting model. And this is what is represented in this figure. First of all, you have alignment onto a low dimensional manifold, and then you can have some structure emerging, for instance, as described by my previous model. I should mention just very quickly that you can do a multi-scale expansion. I'm not showing this in this talk, but you can do a multi-scale expansion where you obtain, at least formally, what the equation modeling the evolution of the particles on the longer time scale after they have collapsed on a lower dimensional space, like in this picture. But this, again, is, I mean, I don't think I have the time to discuss this, and it should appear in Europe's very soon. So with this, let me conclude. I hope I have, sorry for the 5 minutes delay, but I have given you an idea of how interpreting particles, interpreting tokens traveling through the depth of transformers, one can have give some mathematically interesting results about how these models develop some understanding of their input, build representations, which can be in this case interpreted as clusters, and that this framework can still offer some quite interesting open questions, such as the ones I have presented, and there are many other which I'd be happy to discuss offline. So with this, thank you all very much for your attention.